All right, today we're going to talk about something so basic we almost never think about it: motion. But what looks simple on the surface, well, it's actually the key to understanding how the entire universe ticks. So let's jump right in.
So, I want to start by asking you a question, a really direct one. Right now, this very second, are you moving? You're probably sitting down, maybe at a desk, maybe on your couch. So the obvious answer is nope, not at all. But is it really that simple?
You see, in physics, the answer is, well, it depends. It's all relative. Sure, you might be totally still compared to the chair you're in, but that chair is on a planet that's spinning like a top and whipping around the sun at thousands of miles an hour. So whether something is in motion really just depends on your point of view, what scientists call a reference point. Okay, so let's get a nice, clean definition on the table. At its heart, motion is just a change in position over time. If you're here and a moment later you're over there, congratulations, you've been in motion. Simple enough, right? But the real fun, the interesting part, starts when we try to describe how that motion actually happened. And that leads us to our next big question. If an object moves from point A to point B, how do we talk about that journey? Well, physics gives us a couple of really important tools for this, and you'll see they each tell a very different story. Let's break down these two ideas: distance and displacement. The easiest way to think about it is this. Distance is kind of like what your fitness tracker counts. It's every single step, every zig, every zag, the entire path you took. But displacement, that's the shortcut. It's just the straight line from where you started to where you ended, no matter how you got there. It only cares about the start and the finish. Okay, so we've got the path covered. We can describe the journey. But what about how fast something is moving along that path? For that, we need to bring in a new element. We've got to add a clock to the mix. And once you add time to distance, you get a word we all use every single day: speed. In physics, it has a very specific meaning. It's the distance you travel divided by the time it took you to do it. It's purely about how fast you're covering ground. But here's the thing: speed only tells you part of the story. If I tell you a car is going 100 kilometers per hour, you know it's going fast, but you have absolutely no idea where it's going. Is it heading north, south, into a wall? For that, we need something a little more powerful. And that's where velocity comes in. The crucial difference, the big upgrade here, is that velocity is just speed with a direction attached. It doesn't just answer how fast, it also answers where to, and that makes it a much more complete way to describe motion. So here's the bottom line. Speed is what scientists call a scalar. It's just a number. It has a size. 10 meters per second. That's it. Velocity, on the other hand, is a vector. It's the whole package. It's got the size and the direction. 10 meters per second heading east. That little piece of extra information changes absolutely everything. Now, of course, out here in the real world, things almost never travel at one perfect, constant velocity. We speed up, we slow down, we turn corners. Our motion changes all the time. So how do we describe the rate of that change? The answer is a word you've definitely heard before: acceleration. Now, hold on, because most of us hear acceleration and we just think speeding up. But in physics, the meaning is way bigger. It's any change in velocity over a period of time. And that means there's more than one way to do it. In fact, there are 3 ways to accelerate. Think about being in a car. You accelerate when you push the gas pedal. That's speeding up. Check. You also accelerate when you hit the brakes. That's slowing down, or negative acceleration. But here's the one that gets people. You are also accelerating when you turn the steering wheel, even if your speed stays exactly the same. Why? Because your direction is changing. And if your direction changes, your velocity is changing. And any change in velocity is acceleration. And there you have it. That's the toolkit: displacement, velocity, and acceleration. These aren't just vocabulary words. They are the fundamental language we use to describe motion. They answer the 3 big questions: where are you going, how fast you're going, and in what direction, and how is that movement changing moment to moment. And I really want to stress this. This isn't just abstract stuff for a physics exam. Not at all. These are the real deal tools we use to describe and predict how the world works all around us. I mean, this is the language that lets us calculate the path of a baseball, navigate a probe to Mars, and understand the incredible cosmic dance of galaxies colliding. It all comes back to these same core ideas: Which brings us right back to that very first question. But now, maybe it feels a little different. If you're on a spinning Earth that's orbiting a moving sun in a galaxy that's hurtling through space, what does it actually mean to be still? It's a heck of a question, and it shows you just how deep these simple ideas can go. Thanks for tuning in for this explainer.